thinking.
We want to know what the p-value is. We don't really care. The distribution could look like this. And what matters to us is the p-value. Yeah. Now, the mathematicians, they care about this. They care about the formulas. But we're not going to be mathematicians. I have said that when I retire, I'd really like to take some math classes that blew my mind when I was a student, just to see if I can figure things out. But I don't know if I'll do that. Okay, now in the middle of all this, we're going to have assumptions. And one of the things that's happened over the last probably decade to 15 years, because of the software tools, the statisticians who are concerned about the math, they've been able to determine that some of these assumptions that were carved in stone in the past really aren't. And so in some cases we have relaxed views on the assumptions. But for the most part, we really want the assumptions to, we really want to meet the assumptions. That way we can know for certain that the statistical test is appropriate. Yesterday, during Janae's presentation, she talked about n equal 30. That's kind of the standard for how big of a sample size before, and where you start getting that normal distribution if you draw a bunch of random samples. And you might remember that little animation that I showed you. It's illustrating the central limit theorem, which when I was a student and we talked about it, I don't understand this at all, but it's one of those things that slowly it's kind of started to make sense to me. But we have assumptions, and that's what we're going to talk about today. Well, when we put all of these things together, we end up getting statistical findings. And I've already been talking about those. We have a p-value, we have our alpha that we've designated before we start the study, and we can then say what the conclusion is regarding the statistical test, knowing the hypothesis for that statistical test. So we can say we have a p-value less than 0.043, therefore we have, and whatever our statistic is, maybe we have an F statistic and we have some value for that. Therefore, our conclusion is that there are differences between the group means. So when we put all this stuff together, we can come up with our statistical finding. And if the APA book's over there, but if you look in APA, they'll talk about you need to include the statistic, whether it's a T, an F, a wall, whatever it is, and its value. Degrees of freedom is pretty typical in describing the statistic, and APA has a specific way you're supposed to do that. Then you need to include the p-value, and a lot of people put p equal to. No. The best way in general is either p is less than or equal, or p is less than whatever your software gives you. So that's the statistical finding. Now we have to relate it back up to our research objective. And so if our research objective was to compare different training techniques, well, we've got our statistical finding that there are differences, and I probably could put on here for some tests, then you have to go back through and do things like the multiple comparisons. So we can essentially put the results in order. This training group significantly outperformed the other training groups. These two training groups had similar levels of performance, but they were different from this one. And then this group was the poorest performer. So you can describe all that stuff, and you can relate it back to your research objective. We were to compare training, we've done that, here are the results. And that's not typically done in a statistical fashion. You put it back in the language of the person reading the dissertation. You're explaining to them what you found. computer-based hybrid training led to higher levels of performance than any of the other training methods. And maybe you say where the other training methods fell. So it goes back into the language, training methods, what they are, things like that. So it's really important to, at least in your mind and probably somewhere on paper, be putting down the information about some of this stuff. So you can always look at lecture notes, textbooks, things like that as reference sources. Of course, anytime you reference a book or a journal article, you're going to cite that, you're going to include it in your reference list. So, yeah, so hopefully all the parts make a little bit of sense now. You can see how they connect together, and you can start to relate them to the tests we covered in 635 and 760. Now I have to confess, this is a real quick run through statistics. When I was in grad school, I had one class that the entire class was about ANOVA. Wow. I had a regression class. I had a research design class. And so instead of having, or I should say course, an entire course on ANOVA, regression, research design, I had to take 3 courses on the mathematical theory of statistics. My brain about exploded from that one, but fortunately the professor was really pretty neat. So, but we go through these things at a fairly high level really quickly. We don't develop all the mathematical background for these tests, but hopefully you see how to set them up, how to run them, and how to interpret them using SPSS. So that's our goal for 635 and 760. Okay, so common assumptions. We have some of these are just general categories. For example, most of the tests we have assumptions about the scales of measurement, and these assumptions are pretty firmly carved out. We cannot just say, well, this is an ordinal question, but I had 10,000 people answer it, and so I think with 10,000 responses I can compute an average response for that ordinal question. No. If it's ordinal, it can only be treated in certain ways. So you can compute medians. I always tell people if you're dealing with one ordinal question, frequency distributions are really nice because then people graphically can see where the responses were. So the scales of measurement tend to be pretty firmly carved out. Random sample. That one, there are different views on it. A lot of the sampling techniques that you hear about really aren't random. If we're doing a purely experimental study where we have control over everything, you can do a random sample very easily. But we're typically not doing experimental stuff.
I was going to say, random's kind of subjective because how random is random.
Yeah, and it's really within the collection of people who volunteer to be part of the sample, which someone was asking Janae, I think, yesterday about, okay, are the people who are going to respond to this survey somehow different than the people who don't respond to the survey? And I would say yes. The people who don't respond are either not going to understand what's being addressed, or they're going to be thinking, well, that's not part of my job. I don't want to spend even 5 minutes responding to the survey. So within that group, within the group of respondents who agree to participate in the study, we might be able to use random numbers to stick them into individual treatments, but still there is a degree of homogeneity to the people participating.
Did you just note that as a possible limitation?
Yeah, typically you would talk about the fact that you did the study in a certain context, the people responding come from that setting, and that would be one potential limitations. And with experimental studies, we're always trying to generalize back to the population, so it's really important to say, well, these people may not be like the population. And even with a survey, you may talk about non-response bias because people decide not to respond. And I'll confess, when I get a survey, I usually open it up, and when I open it up, it's 1,000, let's not exaggerate that much, but if it's 100 questions that are written so that each question is really asking me about 2 different things or 3 different things, I'm one of those non-responders. And I'm always a little surprised when people invest so much time in building a survey, and especially today, and the questions don't really measure anything. So we have random sample. We have linearity and additivity, and we'll talk about that. Independence, normal distribution, homogeneity of variance or homoscedasticity, common variance across groups. So we have these different assumptions. Now, scale of measurement. I think we've hit most of this. What's the instrument you're using? How is it collecting the data? What are the measures? What are the variables? Because when you look at a survey, at some point you're going to start looking at it and saying, okay, this is a variable. Here's the type of data they're asking for, and it's going to be more or less automatic, especially if you do a lot of survey research. So what type of data? Then what test is appropriate for the variable? For example, correlations. If you're looking at the correlation between 2 ordinal variables, you can't use Pearson's. So in your proposal, you won't just say, I'm going to do a correlation. You're going to say, because these 2 variables are ordinal, I'm going to, and because of this and this and this, I'm going to use Kendall's tau, or I'm going to use Spearman's rho. But you won't just say, I'm going to do a correlation. Because, first of all, the Dr. Brown or I are going to say, well, what kind of correlation are you going to use? Because it's all about what type of data you have. And most of this relates to your research design at a high level. So this is one assumption that you have a lot of control over. So when you're looking at this assumption, or when you're looking at your study, recognize that here you have the control. When that thing goes out, you're literally sitting there every day, probably multiple times a day, looking at how many people responded. Because you're thinking, okay, in my proposal I said I have to have 365 responses. And so you'll find yourself obsessing.